Hello everyone, once again welcome to the session on semiconductors. In the previous session we were discussing about the differences between intrinsic and extrinsic semiconductor. I hope you have listed few differences between intrinsic and extrinsic semiconductors. Moving forward, pure semiconductors are called as the intrinsic semiconductors. Extrinsic semiconductors are the impure semiconductors where the impurity atoms will be added to pure semiconductors. In case of intrinsic semiconductor, density of electrons is equal to the density of holes. In case of extrinsic semiconductors, density of electrons is not equal to the density of holes. Electrical conductivity of an intrinsic semiconductor is low when compared to that of the extrinsic semiconductor. Electrical conductivity is high comparatively in case of extrinsic semiconductor. Dependence on temperature only in case of intrinsic semiconductor. Dependence on temperature as well as on the amount of impurity in case of extrinsic semiconductor. No impurities are added to an intrinsic semiconductor while trivalent impurity or pentavalent impurity are added to extrinsic semiconductor. Band formation in crystal. So, what is the importance of band formation or energy gap in case of conductors, insulators as well as semiconductors? If you consider metals which are considered to be very good class of conductors, the energy gap or energy band is overlapping. So, it is the conduction band and the valence band are overlapping in case of metals. But in case of insulators, there will be a large gap in between conduction as well as valence band, and semiconductors there will be comparatively less energy gap in between the conduction and valence band. So, we know that the electrons in an atom are present in different energy levels. When we try to assemble a lattice of solid with n number of atoms, each level of an atom is further splitted into n levels in case of a solid. The splitting up of sharp and tightly packed energy levels forms energy bands. The gap between energy bands or adjacent bands representing a range of energies that possesses no electron is called as forbidden energy gap. So, in this diagram, we observe that in case of undoped or pure semiconductor, there is a gap between conduction and valence band which is called as the energy gap, and exactly in between conduction and valence band of a pure semiconductor, there lies a energy level which is known as Fermi energy. So, in case of n-type semiconductor, we can say that we observe that the donor level is very close to the conduction band, while in case of a p-type semiconductor, the acceptor level is very close to the valence band. The lowest completely filled band is called the valence band. The lowest partially filled band is called as the conduction band. As I said, metals have overlapping band and therefore no forbidden energy gap is seen in case of metals. So, metals have no forbidden zone. So, there exists no forbidden zone at these higher energy levels. With reference to silicon, the forbidden gap occurs between 3s and 3p shells and has an energy span of almost 1.11 electron volt. In case of germanium, the gap is 0.72 electron volt and occurs between 4s and 4p shells. In semiconductors, conductions happen as a result of thermally exciting electrons in the valence band of crystal. They are able to jump to the forbidden gap and enter the conduction band. So, more and more number of electrons should enter the conduction band. So, this happens when the electrons in the valence band gain some amount of energy. After gaining energy, the electrons in the valence band are able to cross the forbidden energy gap and enter the conduction band. This simultaneously creates an electron and a hole pair which is called the electron hole pair. If an electric field were applied now, a net current would be observed. When the electrons in the valence band jump to the conduction band, vacancy of electrons or holes is created in the valence band. So, here is a little animation where we can observe that on rise in temperature, more and more number of electrons are jumping from valence band to the conduction band. So, what is Fermi level in semiconductor and what is the importance of Fermi level in a semiconductor? The highest energy level that an electron can occupy at absolute zero temperature is known as Fermi level. So, there is almost 50% probability of finding electrons in the Fermi level. The Fermi level lies between valence band and conduction band because at absolute zero temperature the electrons are all in the lowest energy state. The Fermi level changes as the solid are warmed and as electrons are added to or withdrawn from the solid. So, here we can see that in case of metals, the Fermi level is almost overlap, and in case of semiconductor, pure semiconductor, it lies almost in between the conduction or valence band and the conduction band. In case of insulator, we observe that the Fermi level is also again almost in between the valence and conduction band. So, these are the concepts on semiconductor. I hope we have studied about the definition, the types of semiconductor, the doping of semiconductor, impurities added which are the pentavalent and trivalent impurity, and we have also studied about the band gap formation, and finally we have studied the Fermi level and the existence of Fermi level in metal, semiconductor and insulator. Thank you for being with us. Thank you for joining.